Usually, when we think of an automated factory, we picture this huge, sterile hall, right?
Mm-hmm. And an assembly line.
Exactly. Where, let's say, electric cars are built, we want more cars, we add more robots.
Exactly. We crank up the pace of the machines, and more vehicles simply roll off the line.
It's simple, downright linear math.
Yeah, there's no great philosophy to it.
But let's try to imagine a situation where this factory doesn't produce cars, but instead...
Instead, better and better versions of itself.
Exactly, and that's where a huge paradox is born. That's what opens our deep dive today. Because why doesn't cloning the most powerful AI model into, let's say, 300,000 copies make progress 300,000 times faster?
That's a great question, and it's the key to where all of this is heading.
Understanding that puzzle is our main goal today. I've been mulling it over since this morning, and today we're going to break down this mechanism that everyone talks about, the so-called takeoff, liftoff,
Or the ignition point. You know, the intelligence explosion. It's a fascinating moment. Our human linear intuition just slams into a wall of complexity, as if we were trying to grasp infinity.
Today's material is a collection of very dense technical notes. Researchers forecast describing the transition from today's models to self-propelling systems.
Oh yeah, it's easy to get lost in them.
But I have to add an important caveat right away.
So we don't drift off into science fiction.
Right, the documents talk a lot about the year 2027, but that's not a certainty. It's only a forecasting scenario.
Yes, and one based on trends the authors themselves have already revised. Their original model from spring 2025 put the superhuman coder in March 2027. But at the end of 2025, they released a new version of the model, and Kokotailo admitted it's going a bit slower. His median for that milestone shifted toward 2029-2030. On top of that, critics, with the most prominent technical analysis signed under the pseudonym titotal, challenge the very super exponential curve the whole thing rests on. So as we listen to these dates, let's keep in the back of our minds, they're already shifting.
We're going to clearly separate the author's assumptions from the hard evidence, because why analyze this at all? It's these mechanisms that will decide the pace at which the world around us starts to change, economically and technologically.
Absolutely. And the first stage of this scenario, described in our sources, is reaching the level of the superhuman coder.
The superhuman coder. It sounds, well, pretty spectacular, but what does it actually mean? From the material, I gathered it's not just a coding assistant.
No, absolutely not. It's not just a tool that suggests functions to you while you go grab a coffee. We're talking about a model that can, independently write and optimize code better than the best programmers in the world.
Okay, but how does it even drive itself? Because you mentioned a process. Iterative distillation.
Yes, iterative distillation and amplification.
Honestly, it sounds like a process in some refinery.
It does sound complicated, but it's actually a pretty elegant solution. Distillation is simply a transfer of knowledge. You take a gigantic, very smart, but slow and expensive model.
To teach the smaller model.
Exactly. The big one teaches a smaller, nimble model that absorbs the essence of its knowledge. And amplification is the second step of the same loop.
Meaning?
We take many copies and combine them. They collaborate, they verify each other. They build a better answer than a single system would. And that better answer we distill again into one fast model. Amplify, distill, repeat. With each turn, the level rises.
I see. So, an analogy came to mind. It's a bit like running a gigantic corporation. Imagine that managing this fleet of, say, 300,000 copies of the AI is like being the boss of 300,000 brilliant interns.
Yeah, that's a very good comparison.
But they have an enormous workforce, right? They can crank out code day and night. But does that mean smarter decisions? Or do they just carry out tasks faster? They still need some direction from that boss.
And this is exactly where we get into our central paradox. The authors draw a huge distinction between simply increasing the number of processors, the raw workforce, and something they call research taste.
Research taste. That sounds very human.
Because it's that subtle ability. 300,000 copies of your interns. They'll optimize known code at the speed of light, but they won't suddenly pull a brand new neural network architecture out of thin air.
I see, because they optimize what they already know instead of asking new questions.
Exactly. Research taste is asking the right, sometimes non-obvious questions. You look at 100 ideas, you reject 99 and you say, okay, this one path, that's the breakthrough. The AI's raw workforce alone simply isn't enough for the big explosion. Not without that qualitative leap.
And you can actually see this already today. We don't have to wait for the scenario.
Right. In 2026, AI already writes well over 80% of the code at the top labs, like Anthropic. But humans still set the research direction. And the quality of the agents can be wildly uneven. In one July study, the same task took one agent 10 steps, while another slogged through 49. The workforce is already here. What's missing is exactly that taste.
Got it. So that leads us to the next stage. The superhuman coder becomes the superhuman AI researcher. This is no longer just a code cruncher.
Exactly. It designs new tests and architectures on its own. The machine doesn't wait for the engineers.
And this is the moment where two fascinating concepts appear. The first is memory, and the second is this whole Neuralese recurrence. Am I saying that right?
Neuralese.
Yeah?
Recurrence in the Neuralese language.
Right.
It's, well, your mind explodes when you think about it. Because these models stop communicating in English.
They reject human language altogether.
Yes, English or any human language is too slow for them. Way too much ambiguity. They start using their own compressed language, made up purely of neural weights and vectors.
Oh, wow. So they transmit pure mathematical thought to each other.
Bypassing words entirely. Milliseconds, and they know everything.
On top of that comes the memory you mentioned.
Right, because we often see models lose the thread when we chat for too long.
Exactly. The context window runs out. But in this scenario, to be a real scientist, the AI has to maintain full continuity across thousands of experiments. It remembers mistakes from a month ago and immediately corrects the new research.
And that's exactly what creates this so-called R&D multiplier, right? A multiplier that speeds up the whole organization. They learn from their own mistakes in a flash.
Yes, picture it. Thousands of models running tests at the same time. One's failure is transmitted as a vector to the rest in a fraction of a second. No one repeats the mistake.
Amazing. And here it's probably worth giving some concrete numbers, because the authors aren't just hand-waving, they have a whole model. What does this ladder look like?
Glad you asked. The authors build it out of 4 rungs, and they assign each one a progress multiplier. How much faster research goes with AI than without it. They condition the whole thing on the superhuman coder appearing in March 2027. And here's a fun fact. This superhuman coder is, by definition, 30 times faster than the best human and has 30 times more copies. And yet it delivers only about 5 times faster research. Because the experiments still have to run on physical compute, which you can't clone infinitely.
Oh, so there's the answer to my paradox from the start. 300,000 copies, but not 300,000 times faster.
Exactly. And from there, the multiplier keeps growing. The superhuman AI researcher in the scenario August 2027, 25 times. The superintelligent AI researcher, November, 250 times. And full superintelligence in the spring of 2028, a multiplier on the order of 2000.
So from the superhuman coder to full superintelligence.
The median is about a year. And the key assumption of the whole methodology, this blast-off is supposed to happen without adding any computing power to training, purely by improving the software. It's a software-only intelligence explosion.
A year. From a superhuman coder to something that surpasses us at everything.
Yes, the authors, by the way, bring in 2 fictional corporations to ground it for us in reality.
I noticed that. They call them Open Brain and Deep Scent. Am I remembering right?
Yes, just fictional tech corporations caught up in a total bitter research race. And that race forces them into risk. You know, when Open Brain sees that Deep Scent is speeding up, they take off the safeties and let the AI communicate in that incomprehensible Neuralese language.
And actually, I have to stop you here, because reading this, I had a moment of serious hesitation.
Go ahead. What stopped you?
Well, imagine it. These models are chatting in some vector code that's totally incomprehensible to us. They design the tests themselves. They form the hypotheses themselves. How can we possibly be sure this isn't one gigantic loop of hallucination?
Oh, that's a great point. A very astute observation.
How can any engineers at Open Brain know that the AI is actually coming up with something useful and not just, well, talking to itself about some cosmic nonsense that adds up mathematically but makes no real sense?
And the expert's answer to that is very sobering. It's physical verification. There's no getting around it. The model can theorize in Neuralese all it wants, but at the end of the day, that code has to be run on a physical server to see whether it actually sped up the computation.
So it's a collision with reality.
Yes, it brings us back down to earth. And that smoothly takes us to the third section of our analysis, namely the bottlenecks. The places where all this digital magic runs out.
Right, these so-called bottlenecks. Because if the AI is so brilliant, why doesn't progress just shoot off into infinity over a single weekend?
Physics. The laws of physics can't be dodged. The first thing is computing power.
With each new model, you need exponentially more servers, more electricity, more energy. You can't just conjure that out of nowhere.
Exactly. And that ties into the hardware and the production cycle.
And this actually isn't the future. It's the history of 2026.
Exactly. The hyperscalers are planning something like $700 billion in capital spending this year, mostly on data centers, and power is becoming the hard limit. Forecasts point to US data center demand jumping from around 80 to 150 gigawatts. And it's the power grid, not the algorithms, that's the bottleneck.
You know what? I immediately thought of Formula One here. It's like we have a brilliant engineer, the best in the world. And in a simulator, in 5 seconds, they come up with the perfect design for a new wing for the car. And on screen, everything zooms along. But actually building that wing in the factory, you know, out of carbon fiber, is still physically going to take about 3 months. You can't skip past that.
Bullseye. And that leads to the question you also raised, because is this a scenario where the models find a way around these physical barriers? Maybe they optimize the logistics.
They find a new method of producing processors.
Even if they do, building a factory, pouring the concrete, running the cables, that takes human time. You can't optimize it down to 0 in the world of atoms. And that's the powerful break that flattens the curve. Plus the so-called diminishing returns.
Diminishing returns. That concept comes up a lot in this material too.
Yes. Over time, in every branch of science, Each successive big discovery costs more capital, more time, and more energy than the last. The low-hanging fruit has already been picked. That naturally slows down the explosion.
And that in turn leads us to the macroeconomic consequences and to what this means for the world, for us. In the sources, we've got this metric, robot economy doubling times.
The time it takes for an economy based on robots and autonomous agents to double in size.
It sounds dry, but imagine an economy that doubles in size once a year, maybe even faster, instead of every 20 or 30 years.
That's an unimaginable pressure on the entire structure of the world.
Out of this, two completely different endings emerge for us. The authors put it on a knife's edge. We have the race ending and the slowdown ending. Let's think about the race one first.
Well, in this variant, our fictional open brain and deep scent completely ignore the limits. The fight over who creates that AI researcher first is so aggressive that nobody's looking at the costs.
They're going totally off the rails.
They take off all the safeties. The result is a gigantic, lightning-fast jump in productivity and wealth, but at the cost of absolute social destabilization. Nobody can keep up, and the risk of error slips out of control. The slowdown variant, on the other hand,
in the slowdown ending, it's a bit of a different story. The acceleration is still there, but the physical constraints, those silicon factories, that electricity, force this racing train to slow down. Plus, there's international coordination on top of that.
Laws and regulations that cap the amount of computing power for any single player.
That gives the world a chance to catch any kind of breath, even though we're still racing, right? And it's remarkable how it shows us that the choice between this chaotic race and a slower landing depends just as much on human decisions and politics as it does on the technology itself.
Absolutely. And what you just mentioned is treated in the documents as the area of greatest uncertainty.
Okay, I think we need to start tying all of this together. If we were to pull out the 5 most important stops on this timeline,
The main milestones up to the year 2027, right?
So the first point is the creation of the superhuman coder, who writes that superhumanly perfect code.
That's right. Step 2 is the optimization of communication. The models start using their own vector language, Neuralese. They talk without words.
The third milestone. Out of that coder emerges an independent AI researcher, driving the research on its own, with perfect memory.
The fourth stage, probably my favorite, is the moment of the brutal collision of all this digital momentum with the physical, concrete barriers. No electricity, no silicon, and pure, slow reality.
And finally, the fifth, the critical point. The world has to choose how it rolls this out. A full sprint and chaos, or a coordinated slowdown. But the authors remind us that it doesn't have to look this way at all. Because it could veer off track for 2 reasons, right?
Oh yes. The experts give 2 reasons this 2027 forecast might not pan out. First, hard limits. Just a physical wall. It turns out we can't produce that much power, period. There's no getting past it. Second, the algorithmic limit. This is exactly the point. We can clone millions of these coding assistants, but if none of them ever, algorithmically, develops that flash of genius.
The thing I was asking about at the start, instead of a scientist, we'll just get an incredibly efficient archivist.
Yes, they'll endlessly improve old programs, but they won't come up with a new theory of everything. And then the intelligence explosion becomes, at most, well, a small fire in the server room. Progress stalls.
And this is where outside critics come in. It's not only the authors themselves tempering the enthusiasm.
Exactly. The FutureSearch team estimates that the superhuman coder is about 3 times further off than the model assumes, and Andrej Karpathy,
talks about a timeline 5 to 10 times longer. But note, the core of the mechanism, that AI accelerates its own research, is real and already visible. What's disputed is the pace of the escalation, not the direction itself.
That leaves us, honestly, with a really intriguing thought to end on, because if we sum it up, it turns out that in the near future, the development of these most powerful digital beings won't be limited by intellect at all, whether human or artificial. It'll be limited by, well, the physical availability of silicon sand, by how many power plants and copper cables we have.
Incredible. A return to the geopolitics of centuries past.
Exactly. And that's where the question comes up that we want to leave everyone with today after listening to this analysis. It's worth thinking it over completely on your own. Who is really going to control this great intelligence explosion? The one sitting in Silicon Valley who wrote the most brilliant algorithm? Or maybe the one who owns all those physical resources, the cables, the water to cool the servers, and the power plants?
And that's the area to explore beyond our sources today, because the answer to that might surprise us all quite a bit.